Hello everyone. Today we start chapter 4 about limits of functions. That is, chapter 3 is about limits and sequences. In this chapter 4, we extend that idea to the study of functions. So section 4.1 here is about the definition of limits of functions. The goal is to make sense of the phrase the limit of some function f of x when x approaching c is equal to L. Before we go into details, let me make a couple of comments. First, for this definition to make sense, it f doesn't need to be defined at the point C. However, f must be defined near the point C. So this is a very delicate issue. It is actually associated with the notion of a cluster point as defined followed. Let A be a subset of the set of real numbers. A point C in the set of real numbers is the cluster point of A. If for every delta greater than 0, there exists at least one point X in H such that X minus C is smaller than delta. That is, it doesn't matter how small you choose the parameter delta. You can always find a point X which is within delta distance to the point C. So that's why C is called a cluster point or a limit point. Note that A doesn't need to contain the point C as we see in this diagram. However, there is a sequence Hn in A such that Hn different from C and the limit of Hn when n approaching infinity must be equal to C. So cluster point in some textbook is so-called a limit point for that reason. Now we're ready to state the definition of a limit of a function. Let A be a subset of the set of real numbers and C a cluster point. Of A for function f defined from A to the set of all real numbers. A real number L is said to be a limit of f of C if given any epsilon bigger than 0, there exists delta bigger than 0, such that for x in A and 0 smaller than absolute value of x minus c smaller than delta, then fx minus L in absolute value is smaller than epsilon. In that case, we say that the limit of fx equal to L when x approaching c for or f approaching L as h approaching c. This is called the epsilon delta definition. For clarity, think about epsilon as the estimate on the function and delta as the estimate on the point. Whenever you have some epsilon, then there is some delta, such that if x is close, if delta close to point C, then fx is epsilon close to some number L. And this definition should be compared with the limit definition for sequence. The sequence Xn is converging to some number L. If and only given any delta greater than 0, there exists some k, some natural integer k, such that for n bigger than k, Xn minus L smaller than delta. And in this case, we call that the limit of the sequence Xn equal to L. So you can see that the limit definition of a sequence is exactly a special case of a limit definition for a function. It is because a function, a sequence, is just a special function. It is a function from the set of natural integers to the set of real numbers. That's why the definition for functions, for the limit of functions, applies for a sequence. Now we're going to have several equivalent statements about the limit of fx equal to number L when x approaching C. The first statement is using the neighborhood language. Given any epsilon neighborhood V epsilon of L, there exists a delta neighborhood V delta of C such that if C different from X inside the intersection of this delta neighborhood with the set A, then Fx must be within the epsilon neighborhood of the point L. So thinking about this statement as a statement of two levels, the level of the point and the level of the function. At the level of the point, we use the delta neighborhood around this point, around the point C. At the level of the function, it corresponds to epsilon neighborhood around the point L. And it is illustrated by this picture. We consider the point L and the delta neighborhood around the point L is visualized by this shaded band. Now, the statement says that there must be some delta neighborhood around the point C such that the function must be totally within this shaded rectangle. That is, the function, it could be somewhere outside of this delta neighborhood, but as long as the point is within this delta neighborhood, then the function must be within the shaded area. Another equivalent statement is stated in terms of the sequence language. For every sequence Xn in A, the limit of Xn equal to C, Xn not equal to C, then the limit of Fxn must be equal to L. So this is probably the statement that Math explain the relation between the limit of a function and the limit of a sequence. The limit of a sequence is essentially a statement about limit of every sequence satisfying a certain condition. Note that in this statement, delta usually depends on epsilon. Similarly, K depends on epsilon in the definition of a limit of a sequence. Now let me give you several examples to see how the definition works for concrete cases. For example, we consider the function f(x) equal to b for some constant b. So the domain of this function is a full set of real numbers. Let C be a real number, then C certainly is in the domain, and C is a cluster point. We want to show that the limit of fx when x approaching C equal to b. In order to show that, we need to recall the definition. Let epsilon bigger than 0. We're going to choose delta equal to 1. Then for 0 smaller than x minus c in absolute value smaller than delta, which equal to 1, we have the absolute value of the difference fx minus b is equal to the absolute value of b minus b. Because fx is always equal to b, which is equal to 0. And this 0 is certainly smaller than epsilon. That's why the limit of f of x when x approaching c equal to b. And this is not surprising because as you see in this diagram, in this picture, the function here always assume value b. That's why the limit when x approaching c of fx is equal to b. Also, another point to observe is that here the choice of delta is quite arbitrary. Indeed, instead of choosing delta equal 1, we can choose delta equal 2, delta equal 3, and so on. And the same argument is applicable. So this is a very special case when the function is a constant. Now, the next example is slightly more complicated. Let f of x equal to x. Then the domain of this function is again the set of real numbers. Let C be a real number. Then C certainly in the domain. C is a cluster point. We want to show that the limit of fx when x approaching C equal to C. Why? Let's verify the definition. Choose any epsilon bigger than 0. Here we're gonna let delta equal to epsilon. Then for any 0 smaller than absolute value of x minus c smaller than delta, we have fx minus c is equal to x minus c. So in absolute value, this is smaller than delta. And by the choice of delta we made earlier, this is smaller than epsilon. So the intuition is that we try to estimate fx when x is close to c once you write some estimate, then you can choose delta depending on epsilon appropriately. Here is another example when the function f of x equal to 1 over x. And here we follow the same pattern. The algebra is a little bit more complicated because here we had to consider the difference between 1 over x minus 1 over c. And then we had to do some algebraic manipulation. But eventually, we once we have some rough idea how to estimate the function f of x, then we can choose the number delta appropriately. Now, I would like to state a few theorems which are very important in the theory of limits of functions. The first theorem is that a limit is unique, and this is very similar to the situation for the limit of a sequence. Earlier, we stated that a limit of a sequence is unique. That's why we call it the limit. Also, we have a divergence criteria similar to the divergence criteria for a sequence. Let A be a subset of the set of real numbers. F a function from A to a set of all real numbers. C is a cluster point. F doesn't converge to some number L at A approaching C, even only if there exists a sequence Xn in A, Xn different from C, limit of Xn equals C, and limit of f of Xn is not equal to L. So this is essentially just the negation of the convergence statement. The second statement is similar. F doesn't have limit of C even only if there exists a sequence Xn in A, Xn different from C, limit of Xn equal to C, and the limit of Fxn is doesn't exist. So the two statements here are quite similar. The only difference is that in the first statement, we specify a number L. In the second statement, we say the limit doesn't exist. Here is an example, the function f(x) equal to 1 over x. We want to show that the limit when x approaching 0 of f(x) doesn't exist. So the domain of f here consists of the point x different from 0. So 0 is not in the domain, but 0 is still a cluster point. Then we have to use the divergence criteria theorem above, which is equivalent to look for counter examples. And when we examine this statement again, we see that a counter example essentially is a sequence. We want to come up with a sequence that's gonna satisfy the condition stated here. In this case, we consider the sequence as n equal to 1 over n for any natural integer n. It's easy to see that when n approaching infinity, 1 over n approaching 0. This is a very common result we proved in the previous chapter. Now consider yn equal to f of xn, which equal to 1 over xn, which equal to 1 divided by 1 over n. By algebraic simplification, this is equal to n. We see that yn here is divergent at n approaching infinity by the Archimedean property. And you see this Archimedean property appears again and again in this class repeatedly. So the divergence criterion is verified, and the limit of 1 over x when x approaching 0 here doesn't exist. Basically, in summary, we basically came up with a sequence xn approaching 0 such that f of xn doesn't converge to any number. So the divergence criterion is verified. And as a consequence, the limit of the function doesn't exist.